NDT failure. NDT stands for Nil Ductility Transition, and that's going to be the loss of ductility at low temperatures. These low temperatures cause a shift from a ductile material to a brittle one, which then requires less impact energy to cause a failure. Impact energy can be thought of as the energy absorbed in the fracture. A good way to look at this is to use a flow map. We're going to start off with the ductile material, and then we're going to introduce low temperatures, which causes it to become a brittle material. Then an impact energy is going to be occurs, which is lesser than what normally requires a failure, but since we are now brittle instead of ductile, fracture happens. We can see then that the key components of this are going to be temperature, right over here, as well as impact energy, right over here. We can go ahead and use this for a plot then. Figure 1 has impact energy on the y-axis and temperature on the x-axis, which generates a curve that looks like this. We can see right over here, say, there's a point. This has low temperature and low impact energy, which makes sense with our flow map. We'll have a point over here, say, there's a high temperature and a corresponding high impact energy. A key point to note on this curve then is going to be right over here. I'm going to call that point 1, and that's going to be the ductile to brittle transition temperature. So looking down over here, point 1 is the ductile to brittle transition temperature. And this is going to be the temperature at which the fracture switches from being a ductile one to a brittle one, since the material has gone from being ductile to brittle. The way you can locate this on the graph is going to be the point at which the rate of the slope goes from increasing to decreasing, or another way to think of this is going to be the second derivative. It goes from being positive to negative. As you can see up on the curve, that's the point where it switches from increasing to decreasing the rate of the slope. We can then go ahead and label this side of the curve as A and this side as B. A then, looking down here, is going to be below the transition temperature, while B is going to be above the transition temperature. So anything on side A is going to have a temperature that's below, while anything on side B is going to have a temperature that's above. Go ahead and looking at figure 2, we have the same impact energy versus temperature curve, and we'll go ahead and label once again our transition temperature, and we'll have an arrow right over here, let's call that C, and another one over here, we'll call that D. C then is going to be more brittle, and that's because the material has become brittle due to low temperatures. While D is going to be more ductile, and that's because it has not become brittle yet. D over here is still above this transition temperature. That means it hasn't gone through the brittle to ductile phase. This transition occurs in BCC metals as well as polymers. BCC metals at low temperatures have reduced dislocation density, which means it's harder to cause deformation by dislocation slip, while at higher temperatures the dislocations are more mobile, thus allowing for deformation without fracture. We can continue our study on NDT failure by doing an example. Given the temperature impact energy table for a steel alloy below, A, plot temperature versus energy, B, find the transition temperature, and C, determine if the material is ductile or brittle at negative 10 degrees Celsius and 60 degrees Celsius. First off then, we'll start by looking at the table, which we can see in part there, as well as the rest of it over here. And our temperatures range down from 70 degrees Celsius to negative 30 degrees Celsius. with impact energies ranging from 84 joules down all the way to 1.5 joules. For A then, we want to create the impact energy versus temperature curve. So we can see impact energy right over here on our y-axis, with temperature over here on our x-axis. And as you can see, I've gone ahead and made the points already there. We'll just go ahead and connect them for our plot. Each one of these points correspond to one of the points from the table. And looking at this, we can see it's just like our figure 1 and figure 2, with a steep trend over there and then leveling out on each side on these. So that's part A. Next up for part B, we want to find the transition temperature. So like the other ones, we labeled the transition temperature as the point where the slope flips, the rate of the slope flips. So we'll go ahead and label that right about here. We can see it goes from increasing to decreasing, and we'll drop that down to here. This then is going to be our transition temperature, which is right between 30 and 40, so we'll call that 35 degrees Celsius. Finally, for part C, we want to determine if the material is ductile or brittle at negative 10 degrees Celsius and 60 degrees Celsius. So we'll look at the point negative 10 degrees Celsius over here, and we can see that's to the left of the transition temperature, meaning that's going to be a brittle material. And the reason for this is it's because it's left of the transition temperature. It has undergone that change. Looking at 60 degrees Celsius, we can find that once again right over here. And now we can see it's to the right of the transition temperature, meaning it's ductile. And the reason for that is because it's right of the transition temperature and has not undergone that change. We can also go ahead and look at a real-world example. A good one would be a generator shaft. Generator shafts can be pre-warmed initially, and this is done to move above the transition temperature. Looking at, say, a graph, we're going to draw that one more time right over here. This is more prominent, but it still works. That's our transition temperature. If we want to pre-warm it so we can move above the transition temperature, say the point was right here, but by pre-warming it, we could shift our temperature from this spot to this spot, which then goes ahead and gets us above it. We're now ductile, and this is better for our generator shaft. It won't fail quite as easily. It requires a much greater impact energy. Another thing we can do is we can start off by rotating it slowly, and then this is going to go ahead and lower the impact energy initially, meaning that we don't need quite as much impact energy.